Uh, Good soul, everyone, and thank you for joining me today. My name is Sylee Edwards. I'm a systems engineer with a background in spaceflight operations from Embry-Riddle Aeronautical University, and it is my privilege to present the engineering facility for Mission 201. As we take the next steps in space exploration, our ability to design and manage complex systems that support life in an extraterrestrial environment is critical. The engineering facility plays a crucial role in ensuring the safety, resilience, and functionality of the habitat on Mars. In this presentation, I will walk through the key elements of the engineering infrastructure, including internal design, machines and technology, resource management, organizational structure, and some guidelines and protocols that we've established for smooth and safe operations within the facility. With that being said, let's begin looking into the facility's design. As you can see here, the facility is a dome-shaped building that is approximately 8 meters or 26 feet in diameter. The facility has 3 floors, the first one being where the actual engineering activities and work takes place. The second one being the astronauts' living quarters, and the third one being, I like to call it the area for growth. Then that's where the crew will be growing different plants for air purification purposes as well as consumption. Um, so as I stated previously, the first floor is completely dedicated to engineering activities. In this picture here, we can see a computer as well as a workbench um, in which the engineers will use to complete work as well as do troubleshooting and for fabrication purposes. In this slide here, we can see a redundant air purification system, which, especially at this base level where the airlock is located, will remove contaminants such as particulates, bacteria, and so forth. It will also continuously generate oxygen through the conversion of CO2 and ultimately provide the crew with a comfortable environment to work and live in. In this next picture, and probably the previous one as well, you can see a 3D printer. The crew in this facility actually have 2 of these systems so that they can bring their designs to life on Mars. Where sending every tool and system under the sun is unfeasible due to various constraints such as cost, scheduling, and time. Moving on to the second floor, here's a top-down layout as well as a side screenshot of the astronauts' living quarters. You can see that there are 2 bedrooms, a recreational area, that's a ping pong table there, a standard bathroom, as well as a kitchen and a living room. And this is the kitchen in a little bit more detail, where the crew will have access to a pantry, as well as a programmable oven and water purifiers for their consumption. Here is an up-close look at one of the bedrooms. Although it is pretty tight, each bedroom can sleep 2 astronauts because it has bunk beds. On the 3rd floor, we have a designated area for the vertical garden, as well as some basic garden boxes. As you can see here, it's more of like a half floor. It's like a loft. So these plants, which I will talk a little bit more in depth about later, are actually a great source of air purification as well as food. We'll now get into some of the applied technologies in the engineering facility. So in order for the infrastructure of the facility to be built, we will require a heavy lift launch vehicle. And in this case, we'll be using SpaceX's Starship. We will also require autonomous robots such as TARS from Interstellar, or even the Tesla robot that Professor Julio shared with us yesterday, to help do some of the heavy lifting, as well as some excavation and digging through Martian terrain. Alongside that, we'll also need some 3D printing technologies, life support systems, technologies that help with ISRU, batteries, and various energy sources. With that being said, some vital resources to be transported from Earth will most likely be rovers, excavators, drills, 3D printers, life support systems, tools, and some initial supplies. Um, After we get set up on the planet, we can begin exploring how to produce resources such as water and how to use Martian regolith to our advantage. In terms of management, we will employ a crew of 4 different engineers. We will have a systems engineer who will also be the chief engineer, an electrical engineer, a mechanical engineer, and a software engineer. Uh, the reason why I decided that the systems engineer would be the chief is because they generally have a more holistic approach to a system, while other engineering disciplines tend to be more subsystem or component based. The system engineer will be able to facilitate various processes as well as perform system testing to ensure that everything works together nominally, not just component based, because just because one thing works on its own doesn't mean that it's going to work once you put it together with a whole bunch of other systems. With that being said, some of its main responsibilities would have to be having a holistic perspective, knowing how to manage risk, knowing how to perform trade-off analysis, um, and testing. It's the must-haves, and it probably is like the same across all engineers, is to have problem-solving skills as well as the physical fitness level and experience with space-based systems. The electrical engineer will be responsible for reporting to the systems engineer as well as maintaining various electrical systems such as communication systems, robotics, crew support, safety. Similar to the systems engineer, they have to have, like I said, physical fitness, problem solving, have to be able to work in a team, and have to have technical proficiency. The mechanical engineer will also report to the systems engineer and provide structural support and structural expertise to the rest of the habitat. And this can be in terms of communication systems, robotics and automation, life support systems. And lastly, the software engineer must support the development and maintenance of software systems throughout the habitat. They will also be responsible for creating data analysis reports, which will aid in resource optimization. In terms of training, astronauts must undergo psychological, whether that's isolation, teamwork, adaptability, physical, system level, survival, medical, spacewalk, and language training to promote the understanding and just cultural awareness in general. Here are some videos of trainings that all of the participants must undergo. So you can see here we have G-force training, buoyancy training, extreme environment training, which an example of that could be analog missions, social isolation training, airlock safety training, and just general first aid in space. Additionally, each engineer will have their own variation of trainings to do. For example, the systems engineer will have to learn about space system integration and testing, as well as risk management and decision making. As you can see here, the electrical engineer will have to learn how to harness different resources as means for energy production, whether that's wind, as part of like the dust storms that happen in the Martian environment, or solar energy. Here is essentially the same philosophy. The mechanical engineer will have to learn about the different materials that they can use when 3D printing, including using regolith when the earth-borne resources are depleted. Um, You can also see here that the software engineer will have to learn how to code robotics for the space environment. Uh, Regarding food requirements, the average caloric intake for an astronaut is about 3,000 calories a day. Each day, a single astronaut can consume around 2 kilograms of food, which over a period of 5 days amounts to 10 kilograms. When we run the numbers, the crew will need approximately 40 kilograms of food for the entire mission duration. Here's an example of a weekly meal plan. As you can see, it is composed of a lot of freeze-dried and even dehydrated meals. In terms of water consumption, which includes drinking, food, rehydration, for example, using the USOS, which is pictured here, and hygiene, astronauts can consume roughly about 4 liters of water a day, which amounts to 20 liters every 5 days. When we look at the grand scheme of things, the entire crew will utilize about 80 liters for the week. Some key guidelines that other facilities must follow in accordance with the engineering facility is that they must adhere to anything that's related to structural integrity standards and load-bearing guidelines. They must also follow various protocols and standards pertaining to power generation, automation usage, and maintenance protocols. Uh, Protocols. Some daily routines that the astronauts will perform are testing and validation of systems, routine maintenance, documentation and reporting, environmental condition monitoring, water and life support system checks, power and energy system monitoring. In order to maintain the safety of the crew, the astronauts will be given redundant life support systems, as well as fire detection and suppression systems. Um, in addition to that, they will also receive, especially the mechanical engineer, will receive specialized training on hazardous materials. They will also be responsible for establishing emergency escape plans and practicing um, routine safety drills. Regarding entertainment, the crew has a ping pong table or table tennis table. They can play cards, they can use their personal devices. There are also a few different radios that are placed around the habitat so that they can either, communicate or just listen to music. Um, for micro food production, in addition to regular health checks, some ways to keep the small vertical garden operating in the engineering facility include implementing an automated climate control system. They can also use LEDs as artificial lighting, and even using an automated irrigation system so that we can keep track of how much water is actually being allocated to the plants. For 3D printing, using regolith, as Susanna mentioned yesterday, and filament brought from Earth, the engineering facility can print various structural components, tools, life support system parts, furniture, and communication equipment. And now for some spin-offs. Some technological outputs that can be applied to Earth from this engineering facility include water reclamation technologies, waste to energy technologies, and disaster response robots. Some guidelines that can be applied to daily life on Earth include being more efficient with our resources. We also need to implement more contingency planning into our critical systems and practice risk mitigation as much as possible to avoid any errors. The major impacts that the engineering facility will have on the SDGs include clean water and sanitation, affordable and clean energy, uh, industry innovation and infrastructure, and sustainable cities and communities. And here are my references and my personal contact and social media.